You can certainly revise facts too, but it's a different kind of beast. So for example, it's a fact that when I drop things, they fall to the floor. That's an observation about the world. That's not likely to be discarded, you know, if we see it. Now, do we know that the laws of physics are going to be the same tomorrow as they are today? No, not absolutely. But we pretty strongly suspect that that's not going to happen. We couldn't make much progress if the laws of physics kept changing on us. But
so if the whole system of the physics could be changed, the fact could be changed.
yeah, in principle it could. In principle it could. But generally we assume that the laws of physics either aren't changing with time, or if they are, they're doing so very, very slowly. And we certainly get away with that. We can observe galaxies where we're receiving the light from them from billions of years ago, and the spectra of their atoms seem to obey the same laws that spectra of stars in our galaxy do. So that suggests the laws of physics haven't changed for billions of years. So it makes us pretty confident that they're rock solid. That was a more philosophical discussion there, but yes?
So if we were to explain like really simply what the difference between a fact and a theory is, a fact just like more well tested than a theory?
No, so that's more the everyday idea. The everyday idea would be, like an example I'd like to use, Sherlock Holmes first says he's got a theory that the butler did it with the crowbar in the study. And then he gathers information and he says, you know what, now I'm sure not only is it a theory, before it was my theory that the butler did it with the crowbar in the study, but now I know that's a fact. So in everyday English, a fact is something you've established, and a theory is your preliminary guess before you know well. So in other words, the everyday use of the word theory is more like the word hypothesis in science. A theory is closer in everyday language to what we call a hypothesis. No, the difference between theories and facts are the data from our experiences or our experiments, if we're being more specific. And theories are our explanations of those facts. So, for example, Newton's theory of gravity can be used to explain the fact that planets go around the sun on ellipses, and that Kepler's second law is true, that equal areas are swept out in equal times, and that the square of the period is proportional to the cube of the semi-major axis. Newton's law of gravity is a theory, a mathematical theory, where you can solve the equations in it and explain the observed fact that planets go around the sun on ellipses, obeying the law of equal areas, and obeying the harmonic law, the one that says p squared equals a cubed. So theories explain facts. Facts are the data from our experiences and from our experiments and observations. Yes?
So as far as the everyday use of the term, did you say that the theory is similar to hypothesis and fact is similar to theory?
No, so I would say a theory in everyday use of the word theory is similar to the scientific use of the word hypothesis. It's an educated guess, typically. Fact is similar and different from how, so in everyday language, sometimes we use fact to mean something we've observed to be true. Like, you know, it's a fact that if I run into the wall, I'll hurt myself. You know, that kind of thing. We would say that in everyday language too. But in science, we're specifically using the word fact for things like, you know, if you drop something, if you let go of something, it falls to Earth. Planets go around the sun in ellipses. Earth is spinning on its axis. That's what we mean by fact in science. It's the data in science. Yes?
Can we talk about angular resolution and angular separation?
Sure. Any other questions about fact and theory and model and all that sort of thing? Yes?
Do we have a test one for the example?
It could be. It could be. Yeah. Yes? I mean, I'm not saying it is. So the way it works is I always come in, I've already written and photocopied the exam, and my wife always asks after the review session, did they hit the jackpot? Because I won't, there's two reasons to have an exam. One is to get you to study for it, right? The other is evaluative, to see if you studied for it and learned things. And so my wife always says, did they hit the jackpot? In other words, did they ask a bunch of questions that were on the exam? I'm not going to tell you guys who hit the jackpot or not, but I'll tell her. So, right, sir. Yes?
Okay, model be tested by scientific researchers.
So models are, you can test the model. You can make observations to see if your model is consistent with it.
Model is established by scientific assumption or?
Yeah, models are simplified explanations of things or depictions of things that we can test to see if the model would give us useful information about it.
Yes, or?
No, it's based, a model typically you base on your observations. You construct a model to be consistent with what you've observed or with what your theories tell you. Because we can't give every detail about a star, for example. We can't say where every molecule, where every atom inside the star is moving, for example. But we can construct simplifications, like just talking about the pressure and the temperature within the star and so
What seems more than theory?
Theories are explanations. Models are not full-blown explanations so much as they are mental pictures, basically. Yeah. I'm not going to be that mean and ask you to be like, give this perfect definition of a model versus a theory and which one is which and all that sort of thing. So, somebody had a question here somewhere. Yes?
Angular resolution.
Oh yeah, angular resolution. Right. Angular resolution, yes. Yeah, that's in the book. We didn't do it in class, but it is in the book, so let's do it now since we didn't do it in class. I can't cover everything in class. There's just not enough time. But let's talk about that. So the idea with angular resolution is that if you're looking at, say, two stars in the sky, then how far apart they look on the sky is only indirectly related to how far apart they really are from one another. What we can see on the sky is the angle between two stars. And that's true for anything that you're looking at, for example. What I can see of your eyes is the angle between your two eyes as seen from my location. If you're closer to me, the angle from your location between my two eyes will be bigger than if you're far away from me. Similarly, here are two people that are looking at a car driving towards them. What if this car were to go into reverse and back away from them, get further and further away? Notice when the car is back here, the angle between the two headlights is smaller than when the car is closer to them. The angle between the headlights is bigger. If the car kept backing further and further away, would it not be true eventually it got so far away that the two headlights would just look like a single point of light? They'd just be too close together for you to tell them apart anymore. Can you buy that? Yeah. That's the idea of angular resolution. Angular resolution for your eyes is the smallest angle between two light sources where you can still tell that it's two light sources instead of a single light source. It's the smallest angle between two light sources where you can still tell them apart with your eyes. Telescopes, one of their advantages over eyes is that their larger lenses or mirrors give them better angular resolution than our eyes. A telescope is able to distinguish two stars as being separate from one another for a smaller angular separation, a smaller angle between them than our eyes are able to tell. And this is the idea here that this is an actual image of spots of light created by lasers. So here's a situation where you can resolve them, where you can tell them apart. Here is a situation where you use a smaller lens or a longer wavelength. You can't tell them cleanly apart anymore. There's not a clear separation between them anymore. And there's this formula that tells us what the so-called diffraction limit is, the ideal angular resolution, smallest angle you can tell apart for a given wavelength of the light and diameter of the telescope. And it says it's this number, 2.5 times 10 to the 5th arc seconds, times the wavelength of the light divided by the diameter of the telescope. So if the wavelength gets bigger, what happens to the diffraction limit? Does it get bigger or smaller? If the wavelength gets bigger, it's up in the numerator, so if I make the wavelength bigger, the diffraction limit gets bigger, and if the diameter of the telescope gets bigger, that's down in the denominator. Does the diffraction limit get smaller or bigger when the diameter of the telescope gets bigger? Smaller. Now, diffraction limit, angular resolution, is like golf in that I've heard it described, I really like this. The object of golf is to play as little golf as possible, right? In other words, the person that wins is the person who takes the smallest number of shots to make the 18 balls go in the hole. So the less golf you play, the better you did at golf. The object of golf is to play as little golf as possible. Smaller is better when it comes to golf scores. Similarly, smaller is better when it comes to angular resolution, because notice, angular resolution is the smallest angle you can tell apart. And so the sharper your eyes are, the smaller that angle will be, the finer the details that you can see. And this comes to the idea of like phone displays, for example, or laptop displays. Apple is the first one that started mass manufacturing what they call retina displays. Other manufacturers call them high DPI displays. And the idea with a retina display is that the pixels, the individual elements in the picture, are so close together that when held at normal viewing distance, they are closer together than the angular resolution limit of your eye. They're too close together for your eye to tell them apart. And this is an example of a magnified view from a display that does not have that property. If you held a phone like this at arm's length, you would be able to see the pixels. You'd be able to see the individual elements because they're further apart in angle than the smallest angle that your eye can tell, the angular resolution of your eye. But on a so-called retina display or high DPI display, hold it at normal viewing distance, and you can't see the individual pixels. They all smoothly blend together, and that's because they are closer together in angle than the angular resolution limit of your eye. So smaller is better when it comes to angular resolution. The finer details you can see correspond to smaller angular resolution. You want that angle that you can distinguish to be as small as possible. That means finer details that you can see. Yes?
So when Apple pretty much says that they're like making their retina display better, it really doesn't matter because there's only a certain point that it can get to.
Yeah, that's correct. So after a while it gets to be height. In other words, if they make an even finer grid on it, what that means is you could hold it really close to your eye and not be able to see the pixels. But you don't typically hold the phone this close to your eyes. I mean, I kind of say, once you can't see the pixels from a foot away, then it's just turning into height to add more and more pixels to the display. Then you're just paying extra money, and you're not going to notice any improvement after that point. Yeah. Or you can have a magnifying glass and say, wow, look how tiny those pixels are. Wow. But that's kind of, yeah, congratulations, you're throwing money out the window after a while. Yes?
I'm not entirely sure what the difference is between arc minute and arc second.
So yeah, so they are measures of small angles. So we all know that 1 degree is what fraction of a circle? How many degrees in a circle? 360. So 1 degree is 1/360th of a full circle. One minute, and that's the way we, so if you're a carpenter, that's like 1 foot. But in terms of angle, that means 1 arc minute. And a minute is related to a degree the way a minute of time is related to an hour of time. 1 arc minute is simply 1/60th of a degree. It's just a small angle. It's 1/60th of 1 degree. And 1 arc second is 1/60th of a minute, or 1/60 times 60 of a degree, 1/3600th of a degree. So arc seconds are a way to express very small angles, 1/3600th of a degree. The moon is in our sky about half a degree wide, which means it's about 30 arc minutes wide. So if you want a sense of it, the moon is about 30 arc minutes across. The angular resolution of the human eye is about 1 arc minute. So you can see things on the moon that are bigger than about 1/30th of the size of the moon from Earth. That's not good enough to see craters on the moon with your naked eye, but binoculars or a telescope have better angular resolution than your eyes do, and so if you look through them, you can see finer details. You can see smaller features on the moon because they can do better than 1 arc minute, 1/30th of the angular size of the moon is seen from Earth. There are birds of prey who need to be able to see little critters as they fly high above them over valleys or whatnot. And we can't ask them, they don't speak English, but they have, part of what sets the angular resolution of our eyes is how densely packed the cells are in our retina, the light sensitive cells. Those birds need to have very fine vision, and so their cells in their retinas are packed more closely together. You do the calculation, and there are birds that can see craters on the moon. Pearls before swine, they're not like, wow, I can see craters on the moon, rock. They don't know what they're seeing, but that would be cool to be able to see craters on the moon. There are birds whose angular resolution of their eyes is so much better than ours that they can see craters on the moon just looking at the moon. Yes?
So, something that has angular resolution in an arc second has better resolution than an arc minute?
Yes, because an arc second is only a 60th of an arc minute. So if your angular resolution was 1 arc second, and a backyard telescope under typical twinkling conditions can do about 1 or 2 arc seconds of angular resolution, well, that's like about 60 times better than your eye can do. You can see things on the moon through the telescope that are only 1/60th as big as what your eye can see, which is why you can see a lot more detail through the telescope than you can with just your eye. It has the ability to see much finer detail than your eye does. Yes?
So if we have to convert so like distance to like seconds or something like that, or like whatever it is, will you give like the matrix scale or?
I will have a formula sheet so that any formulas that you need will be on the sheet. You need to know how to use them, but I will have a formula sheet. Yeah. I will just tell you, I'm not going to have anything where I have you calculate angular size from distance and linear size. I don't happen to have anything on this exam about that. So. Yes?
Could you explain what it means to say that Newton's law of gravity is the inverse square law?
Yep. So, we've had like this law right here, what we were talking about. So the question is, what does it mean to say Newton's law of gravity is the inverse square law? So this is one where it's not inverse square, it just goes like the square. But Newton's law of gravity is inverse square because the distance squared is down on the bottom in the denominator. So that means that if we've got two bodies, this one's mass m1, this one's mass m2, the distance between them is d, then Newton's law of gravity says they're each exerting a force on the other, equal and opposite forces, each on the other, of that universal constant g times mass 1 times mass 2 divided by the distance squared. Inverse square law means the distance is squared and it's in the denominator. That's what it means. The inverse means it's in the denominator. Squared means it goes like the second power of the distance. And so here, in other words, if d becomes, let's say, 3 times larger, if I take these two bodies and make them 3 times as far apart as they were before, and the question is, what happens to the force of gravity? What happens to F? Yep, it definitely gets smaller. It gets smaller because they got further apart. How many times smaller? Now, 9 times smaller, because it's 3 times bigger d is. So what we have to do is take 3 squared, so it becomes 9 times smaller. If d gets bigger, the force gets smaller. Another way to think of it would be the force becomes 1 over distance squared, the force becomes 1 over 3 squared equals 1/9 as large as before. And those are 2 ways of saying the same thing. In other words, we use 9 times smaller to mean 1/9 as large. They both mean the same thing. So you could either say that it's 9 times smaller or only 1/9 as big as it was before when you triple the distance between them. So with an inverse square law, the difference is that it gets bigger when the distance gets smaller and gets smaller when the distance gets bigger, but it's still a square law. You still have to square what happened to the distance in order to figure out what happened to the force. So that's how the inverse square law works for gravity. Yes?
Does that mean that one of the masses gets larger and the gravitational force gets larger?
It does, yeah. So if I made M1 5 times bigger, and I kept M2 the same, and I kept the distance the same, all I changed was M1, what would happen to the force? You'll get 5 times bigger, yep. If I change either mass and hold everything else constant, that by itself makes it get bigger by whatever I change the mass by. If I made M1 5 times bigger, then the force would get 5 times bigger as long as I didn't change anything else. Yes?
Does that mean that if you double the mass of both points, does that mean the gravitational force gets increased 4 times?
It means exactly that. If I double both of the masses, it gets 2 times bigger because of M1, but another 2 times bigger because I doubled M2. So it would be 2 times 2 times as big as before, or 4 times as big as before. Yes, that's exactly what it means. Yes?
What does it mean to say that a physical quantity like energy is conserved?
Conserved, yeah, unlike in politics where, if you're conservative, it means that you want to keep society the way it is, and you vote Republican and all that sort of thing. In physics, we have a different meaning for it. If something is conserved in physics, it simply means it stays the same. So if energy is conserved, it means it's the same before as it is after. It's neither created nor destroyed, but it might be changed into different forms. So conserved means staying the same in physics. So before and after, there's no change overall, although things can change, but the total amount of energy stays the same. It might be converted to different forms, but the total amount of energy stays the same. Yes?
Can you talk to me about Kepler's law?
About whose law?
Kepler's.
Kepler's law, yeah, so there's 3 of them, right? Right? So we did Kepler's first law earlier, that's where we said that the orbit of a planet is an ellipse with the sun at one focus. And then there is also Kepler's second law, which is the one that says that the orbit, that the line from the planet to the sun sweeps out equal areas in equal amounts of time. So that was this one here, where if the planet goes between 2 points on the orbit, then the area swept out by the line from the planet to the sun means this area right here. It'd be like if you had a stretchy rubber band that you can imagine was laying paint down as the planet went around the orbit, even though there was nothing to paint. That would be the area swept out. Here's the area swept out when the planet went from here to here. Kepler's second law says if those areas are equal, the times are equal, and vice versa. If they're not equal, then the areas aren't equal. If this area was twice as big as this one, then it took twice as long to go between those 2 points as it did between those 2 points. So whatever, if one area is bigger, then it also took that many times longer to go between those 2 points on the orbit. So that's Kepler's second law. Be sure you've looked over the lecture tutorial where we're doing various examples of Kepler's second law going around the orbit and so forth. And then the third law is the one that says p squared equals a cubed, where p is how long it takes to go around the sun in years, and a is the length of the semi-major axis, half the long axis of the elliptic orbit, in terms of Earth's value, in terms of astronomical units, Earth's value of a, the semi-major axis. And so for all the planets, if you square the period and cube the semi-major axis, those 2 things are equal to one another. Those 2 numbers will be equal. Yes?
What is a black body?
What is a what?
Black body.
Black body is the things that we're describing with the Stefan-Boltzmann law and with Wien's law. So a black body is an ideal, hypothetical, perfect emitter and absorber of radiation.
What's the observer mean?
To absorb is to, what? Is to like swallow it and not give it back, so to speak. So if I absorb something, I swallow it. I get rid of it. So the idea is, if this was a perfect black body, any photon that hits it, it eats it. It's gone. It eats the photon. And if it absorbed every single photon that hit it, it would be a perfect absorber of radiation. It also gives off photons, but only after it eats other photons, so to speak. And if something were a perfect black body, I mean, the board is black, but I know it's not a true black body, a perfect black body, because if it were a perfect black body, it would be like looking at a black hole. No light would be coming to you from it at room temperature where it's not hot enough to give off visible light. There is a substance called vantablack that is the closest thing we've created to a true black body. And I'll see if I can just find a picture of it here. Yeah, so, I mean, it's pretty cool. And so BMW, just to show off, made a car that painted it with this stuff. So you can kind of get a sense of it. It's just so black. Look how black that is. It's very close to a black body, this material. Not a real black hole, but it's really as close as you can get as we got into a black hole. So, okay, enough of that. I just like, if you look up vantablack, you can see pictures of it. I'd like to see it in person, but it's just really, really, really dark, and they're BMW, so they had to show off. It's something that's black, basically.
So So you said it was a perfect absorber and
And emitter, and by perfect emitter, we mean it gives off a spectrum, a plot of brightness versus wavelength, described by those curves that we showed before. There's a specific mathematical formula that we don't need to worry about. But when you plot that mathematical formula, you get those curves that we were showing before, these guys right here. It's perfect in the sense that if for a given temperature, it has a curve that only depends on its temperature, not on what it's made of, and it has this particular characteristic shape, which is a plot of a certain mathematical function.
So it doesn't have emission or reflection lines?
No, it has no emission or absorption lines. Yeah, it would have no emission lines and no absorption lines if it's a perfect black body. It would have a pure, continuous spectrum if it's a perfect black body. So no star is a perfect black body. They've always got absorption lines. They're only approximations to black bodies. Yes?
Can you go over imaging, spectroscopy, and time monitoring?
Yeah, imaging, spectroscopy, and time monitoring. Can I go over imaging, spectroscopy, and time monitoring? So those are the three types of observations that astronomers can make. Imaging is just what it sounds like. It's basically taking photographs, taking pictures of what it is that you are trying to study. Spectroscopy means using a diffraction grating or a prism in order to spread light into its colors so that you see things like, for example, here is the sun's spectrum. It's actually folded over many, many times so that we can see it in very fine detail. So that's where you spread light into its component colors, and you can look for spectral lines at specific wavelengths that you can measure. What do the wavelengths of the spectral lines tell you? They tell you what it is, what it's made of. So spectroscopy allows us to tell what something is made of. We'll also see that how strong, how dark the various spectral lines turns out also is a clue to the star's temperature. So spectroscopy is spreading the light into a spectrum so that you can carefully measure how bright it is at different wavelengths. Time monitoring is to keep observing an object to see how it is changing over time. And so a very common thing to do with time monitoring is to keep measuring a star's brightness over and over and over again so that you can make a plot of how the brightness changes with time. And so the two kinds of observations can overlap with one another. In other words, for example, I was telling you guys about my own research, which involves star spots. And so let me pull up an image that I showed, or a figure that I showed you guys. An example of where my students and I use time monitoring to study star spots on a star called Lo Pegasi. This is an image of Lo Pegasi, and what we do is we take hundreds of images of Lo Pegasi over and over and over again, and each of those images we measure how bright Lo Pegasi is compared to this star right here, whose brightness is known to be constant. And so it's both, we're using imaging to do time monitoring, because what we're doing is seeing how the brightness of the star changes with time. That's the time monitoring part of it, and we're using imaging as a tool in order to do the time monitoring. And that's essentially what the three things are. Taking pictures, seeing how something changes with time, that's time monitoring. Imaging is taking pictures, and spectroscopy is spreading the light into a spectrum, into its component wavelengths, and measuring things like how bright it is at different wavelengths, where there's spectral lines and stuff like that. Yes?
Could you explain the concept of knowing what direction the acceleration vector points in uniform circular motion?
Yeah, in uniform circular motion, it points towards the center of the circle. And here's how you can tell that. One way is you pick up your little sister and you swing her around you like this, okay? As you swing her around you, she's, if you're doing a good job, moving in uniform circular motion around you. Now, if you let go of her so that you stopped exerting a force on her, would she keep would you keep moving around in a circle? Nope, she'd fly off and run to mom at that point. So you need to exert a force on her just to keep her moving in a circle. And now ask yourself, if I'm doing that to little sister, do I need to push out on her or pull in on her? I gotta pull in on her. And that's telling you that the force you need to exert on her to get her to move in a circle is inwards towards you, in towards the center of the circle. And that's exactly right. The force in uniform circular motion is inwards towards the center of the circle. And when it comes to orbits, if you think of something moving in a circle, orbits are usually ellipses, but if something is moving in a circle, for example, Earth goes around the sun very close to being in a circle, the idea is the sun's gravity is what is applying that inwards force on Earth towards the sun to keep the Earth moving essentially in a circle around the sun. Yes?
Could you explain how much more radio telescope can be used to achieve resolution?
Yeah, so that's, you're asking about interferometry with radio telescopes.
How do you calculate?
Well, the details are pretty complicated. The details are not something I'm going to worry about having you be able to do the calculations of, because that's like graduate school material. You have to, each observation allows you to compile what are called the visibilities, which are components of the Fourier transform of the intensity distribution on the sky, and then you perform the inverse Fourier transform, but you have to apply inversion techniques in order to clean things up. And none of that's making any sense to anybody because it's very advanced math that we don't have to worry about here. Right, I want you to understand qualitatively the following, okay? This is an example of, this is the very large array, it's an interferometer. And the idea is this, it turns out that by doing math, you can take signals from widely separated radio telescopes, and these days it's becoming possible to do it with infrared telescopes as well. You can take signals, you can combine signals from widely separated radio telescopes, and by doing mathematical processing on them, you can get an angular resolution which is the same as if you had a single gigantic radio telescope whose diameter was equal to the distance between those much smaller radio telescopes. And so, for example, often we use very long baseline interferometry, which means we have radio telescopes on separate continents. And when we do that, we can make an angular resolution, which is like we had a huge, giant radio telescope thousands of miles across without having to actually build a telescope that's thousands of miles across. And so it's a very useful technique to make finely detailed images of the sky at radio wavelengths. Yes, just a second. So you were saying?